Starting today, we will begin our special session on non-local turbulence modeling up to 21st of June. It remains my great pleasure to introduce today Professor Fujihiro Hamba, who is one of the early people to look into non-local modeling of turbulence. Professor Hamba is a full professor in fluid physics at the Institute of Industrial Science, the University of Tokyo in Japan. He studied physics and received his PhD degree from the Graduate School of Science, the University of Tokyo in 1990. His research interests are physics and modeling of inhomogeneous turbulence, including non-local transport of turbulence, Reynolds average Navier-Stokes equation model, and large eddy simulation, and dynamo effects in magneto-hydrodynamics turbulence. Professor Hamba, it's a great pleasure to have you. You may please begin your talk.
Okay, thank you, Pavan. It's my great pleasure to give a talk to you today. And first of all, I must say that in my approach, fractional calculus was not used. Instead, a non-local approach was taken where space and time integration was used. So the outline of today's talk is as follows. So after the introduction, I briefly describe what is turbulence modeling. Then the main contents, evaluation and modeling of non-local eddy diffusivity. Okay, then let's start. Not here. Okay, so this expression is the eddy viscosity, eddy diffusivity approximation for the turbulent heat flux. So left-hand side is the heat flux due to turbulent motion, and right-hand side is the mean temperature gradient term. So we often assume that heat flux is proportional to the mean temperature gradient, and down the gradient direction, heat flux is driven. Then this approximation is widely used in turbulence modeling. This model is, in some sense, local, in the sense that the turbulent heat flux at one point, one location, is assumed to be proportional to the temperature gradient at the same position. But such a local approximation is not trivial. So rigorously, the condition for good approximation is as follows. That is, the length scale of mean field variation, I mean mean scalar, mean temperature gradient, should be much greater than the turbulence length scale of turbulent fluctuations, which leads to the eddy diffusivity kappa T. So my interest is the local approximation valid in real turbulence, and actually, in the meteorology field, I mean, especially in the atmospheric boundary layer, some non-local model were used already. So this picture is just a schematic plot of the convective atmospheric boundary layer. So this is a layer, say, about 1 kilometer height. The bottom, this is just a surface of the Earth and heated. Then we can see some large thermal convection, and you can see some large eddies. And also, this solid line means the mean temperature profile. So this suggests that the length scale of mean temperature is as large as the thermal convection or turbulent fluctuations. So the scale is nearly, the two scales are nearly the same. So the local approximation is cannot be valid. So some non-local approach was already proposed. For example, the first expression is that theta is the mean temperature. So time evolution of mean temperature is written in terms of the mean temperature at all locations of y. Y is the vertical location. So that time evolution of mean temperature at height yj is dependent on all location temperature like this. And also the next expression means that this is just a straightforward extension of the Eddy diffusivity model to non-local model. So by using the space integral. So which means that scalar flux at y, location y, depends on also mean velocity, mean temperature gradient at different position of y, say y prime. So I'm interested in the second approach. And in my previous work, using the Green's function, I theoretically derived an exact expression for non-local eddy diffusivity. And such diffusivity and also viscosity were evaluated using three-dimensional simulations of atmospheric boundary layer and so-called turbulent channel flow. And of course, this is just a few approach, but recently a non-local approach was also proposed using, say, recently machine learning and also fractional calculus. And I, by myself, revisit this non-local research. And very recently, I carried out a simulation of homogeneous isotropic turbulence, basic turbulence, with inhomogeneous shear, inhomogeneous scalar, I'm sorry. And a model for non-local eddy diffusivity was proposed and analyzed carefully using by following statistical theory of turbulence. So the first part is just an evaluation of non-local eddy diffusivity, and second part is just a modeling of non-local eddy diffusivity of this main part of my talk. Okay, then, so first I briefly explain about turbulence modeling. So the following equations are the Navier-Stokes equation for velocity and convection diffusion equation for scalar. Scalar such as temperature, humidity, or some concentrations of some chemically reactive species, and so on. And here, when deriving the diffusion equation, the relationship for scalar flux is used. The scalar flux is proportional to scalar gradient like this. And actually, even for turbulent flows, the velocity motion and also scalar transport were governed by this equation. So, and also the right figure shows the some typical wall-bounded turbulence. It is a vertical motion near the wall of turbulent channel flow. And in direct numerical simulation, DNS, the above equations are numerically solved. So basically, the solution is unsteady, three-dimensional, very complicated velocity and scalar field. And owing to very large computing cost, DNS is limited to flows rather at low or moderate Reynolds numbers. But of course, DNS is a very powerful tool for fundamental research of turbulence, just like a numerical experiment. At the same time, for practical flows at high Reynolds numbers, some turbulence modeling is required. So for turbulence modeling, some averaging is introduced to divide the velocity and scalar into mean part and fluctuating part. So for example, capital U is the mean velocity, and lowercase u is the velocity fluctuations, and bracket denotes the ensemble average. Then, for example, this example is channel flow. It is, of course, unsteady, complicated, three-dimensional flow. But after averaging, ensemble averaging, it is just a quantity, only depends on the y coordinate, say, wall normal coordinate only. So mean velocity profile is just a simple figures like this. And the following equations are the mean velocity and mean scalar equations. So, for example, in the mean velocity equation, unknown quantity appears. This is called the Reynolds stress, say the correlation between velocity fluctuations. And also in the mean scalar equation, another unknown quantity appears called the turbulent scalar flux, like this. So turbulence modeling implies that these unknown quantities needs to be modeled. I mean, it needs to be expressed in terms of the non-mean field in order to close the system of equations. And in this talk, we focus on the turbulent scalar flux, like a turbulent heat flux, because it is rather straightforward because of the linearity of scalar in the equations. Okay, then as I mentioned, this Eddy diffusivity model is widely used. Here, kappa T is called the Eddy diffusivity, which represents the diffusivity enhanced by turbulent motions. And this is proposed by analogy with the molecular scalar flux I mentioned before. So this molecular scalar flux is also assumed to be proportional to the temperature gradient. And kappa is the molecular diffusivity. And this expression is known to be very accurate. This is because the molecular motion, the length scale of molecular motion is much less than the scale of macroscopic temperature field. But as I mentioned, in the turbulent heat flux, the two scales cannot be separated so much. Anyway, if we substitute this widely used Eddy diffusivity model into the mean scalar equation, then we obtain this equation. So you can see that just the kappa T is added to kappa molecular diffusivity. So this clearly means that diffusivity is enhanced by turbulent motions. And for, in general, for developed turbulence, kappa T is much less than kappa. Oh, I'm sorry, much greater than kappa. And just a reference, in one of the turbulence model, so-called K-epsilon model, kappa T is further modeled, expressed in terms of turbulent kinetic energy K and its dissipation rate epsilon. This is just a example of modeling kappa T and also Eddy diffusivity model. So this is just a simple diffusion equation, although kappa T can vary in space and in time. Then next I will explain about the non-local approach using non-local Eddy diffusivity. So in my previous work, I just start from the scalar fluctuation equation. Lowercase theta is the scalar fluctuation, and its equation is written like this. And here, on the right-hand side, there is a term of mean scalar gradient. Say this is capital theta. So we can consider that this term effectively a source term for temperature scalar fluctuation equation, theta equation. So this is like a heat source term. Then when we consider the Green's function for the left-hand side operator or response function for scalar fluctuation, G here. And in the equation for G, right-hand side is just replaced by delta function like this, and which means that in this case, a source is emitted only at one position x prime and at one time t prime. So this is just a delta function like source term. And for later convenience, UI velocity fluctuation is already multiplied by considering this source term. Okay. Then if we obtain the profile of GI, Green's function, then we can obtain a formal solution for scalar fluctuation, theta. So theta is can be written in terms of the space and time integral of mean scalar temperature, mean scalar gradient like this using Green's function GI. And using this formal solution, we can write down the non-local expression for the turbulent scalar flux like this. So not only space integral, but also time integral is used. And kappa NL, we call it non-local Eddy diffusivity. This is the function of not only xt, but also x prime and t prime. So this expression is the, say, main expression of today's talk. Okay. Then, which physically means that scalar gradient, say mean scalar gradient at position x prime and t prime affects heat scalar flux at position x and t, which means that both spatially and temporally non-local expression. And the non-local Eddy diffusivity is expected to have a non-zero value if separation x minus x prime is equal to or less than some turbulence length scale L, or time difference t minus t prime is equal to or less than some turbulent time scale. Okay, so then if in such a region of non-zero kappa NL J, mean scalar gradient is nearly constant, then this scalar gradient means scalar gradient can go out of integrals. So we can obtain this local approximation like this. Here, kappa L is just a integral of the non-local eddy diffusivity. So mean scalar gradient is nearly constant, means that the length scale of mean field variation is very, very long. So if such a condition holds, then this local approximation is valid. But as I mentioned, in real turbulence, this condition is not good. Doesn't hold. So if non-local eddy diffusivity model is substituted into the mean scalar gradient, then mean scalar equation is written like this, a kind of differential integral equation. Okay. So then first I evaluated the non-local diffusivity using the DNS of turbulent channel flow. So turbulent channel flow is flow between the two flat plate, and pressure gradient is applied in the x direction, mean flow direction. And statistical quantities are inhomogeneous only in y coordinate. So y coordinate is normalized by the half the channel width. So the bottom wall is located at y equals -1, and top wall is located at y equals 1. Okay. And in this for this channel flow, the evolution equations for ui, theta, and also gi were numerically solved. And here I will show the result of 3 cases. So the first 2 cases, case 1 and case 2, the boundary condition is just a 0 scalar, and source term is applied. Say, for example, case 1, uniform source is added in the whole domain. Okay, and in case 2, near the center region, source term is applied. And in case 3, there is no source term, but the value of scalar at bottom wall varies in x directions, like this sine function, using sine function. Okay. Anyway, then in cases 1 and 2, this is just a one-dimensional statistical quantity. So this is the profile of mean scalar. So in case 1, this is just a simple, I'm sorry, this is just a distance from the wall, is denoted by y plus. So apart from the wall, the temperature or scalar is has large values. And in case 2, due to the concentrated heat source, scalar source in the center region, so the mean scalar profile has a steep gradient in the center region. Okay. Then the left figure shows the same profile of mean scalar, but this is the scalar gradient like this. So in case 1, you can see steep gradient near the wall at y equals -1 and y equals 1. But gradient gradually changes in the main center region. In contrast, in case 2, the mean scalar gradient rapidly decreases at the center region, like this. Okay, anyway. Then right figure shows the evaluation of the non-local diffusivity using the Green's function. So this is this profile is a function of y prime. So and also I need to explain the following expression. So in this turbulent flow, so the scalar flux is just a function of y, or normal coordinate only. And integral is just a y integral like this. So kappa NLYY represents the contribution of the scalar gradient at y prime to scalar flux at y. So, for example, this small dashed line represents the contribution of the scalar gradient at various y prime positions like this to the scalar flux at position y equals minus 0.48 or something like that. So you can see that the profile is very broad, wide. I mean, effectively, whole position of the bottom channel, half channel is affects the turbulent flux here. If this non-local diffusivity profile is as sharp as the, say, Dirac delta function, then the local approximation is very accurate. But clearly show that the non-local diffusivity has some wide profile. Then I will show the resulting scalar flux. So basically, I showed 3 lines. Say, the first is the present DNS means the accurate value directly evaluated by DNS results. So this is accurate. And non-local means that, I'm sorry, non-local means that using this non-local expression, and the local approximation is like this. And you can see that the 3 curves I'm sorry, the non-local value and present DNS value are very agree with each other like this. Not only for case 1 and then even for case 2. And you can see the local value has some deviation here, and also large deviation from here. So for example, in the center region of the case 1, non-local value is not so bad. This is because mean scalar gradient has a very large length scale here, except for the near wall region. But for case 2, the length scale of mean scalar gradient has even short length scale. So this is why the local approximation really overpredict the heat flux, scalar flux like this. Okay. So anyway, non-local expression was validated using the DNS. And I will show two-dimensional profile here. So in this case, in case 2, there is no source term, but the boundary value are changed using sine curve. So the mean scalar near the bottom boundary changes like this. And this figure shows the two-dimensional profile of the non-local diffusivity, kappa NL. Okay. So in this case, we plot the profile function of x prime and y prime. Okay. So this figure shows the some dependence on the upstream region. So you can see not only wall normal direction, but also streamwise x direction, clearly non-local contributions here. And also, when the position is apart from the wall, then turbulent has more larger length scale or more high mean velocity profile. So such a high velocity means that downstream direction is elongated like this. And sorry, I should mention that the non-local expression can be written like this using a two-dimensional space integral. Okay. And the resulting scalar flux are like this. So you can see the periodic profile of scalar flux into xy planes. And you can see that the DNS result of scalar flux and non-local expression are agreement each other. And also local expression overpredicts the scalar flux like this. So the same trend, same situation as the case 1 and 2. Okay. And also, I should mention some standpoint of non-local model, just briefly, using some simplified transport equation for scalar flux, like this. So although I can write down the exact transport equation for scalar flux, but here I start from the simplified equation. Say this is the production term accompanying with mean velocity, temperature, mean scalar gradient. And the second term is the dissipation term, or using the relaxation time or turbulent time scale term. And the third is the diffusion term. Kappa T is the turbulent diffusivity. Then we can understand the local and non-local model as follows. When we assume that the steady state and also zero diffusion, which means that the left-hand side and third term on the right-hand side is neglected. Then just by balance between the first term, production term, and the second term, dissipation term, we can obtain the local eddy diffusivity model like this. And the eddy diffusivity is just a product of the time scale and Reynolds stress or kinetic energy like this. And if we assumed steady state, but non-zero diffusion, so we keep the diffusion term, so which leads to some non-local effect in space. Then using some Green's function of this operator, we can write down a formed solution. Say Qt scalar flux is written in terms of the space integral of mean scalar gradient. So we can understand that if we keep the diffusion term, then non-local effect is incorporated, and this non-local integral expression can be obtained. And also in this in my approach, also time derivative term also kept, and we obtain not only space integral but also time integral is involved. Okay, this is just a summary, just skip. But at that time, modeling of non-local eddy diffusivity had not been developed. So very recently, I revisit this topic and try to model this non-local eddy diffusivity. So the last example is just a non-local diffusivity for channel flow, turbulent channel flow, but it is rather difficult to model it from the beginning because of the anisotropy and inhomogeneity of turbulence. So I just start from the homogeneous isotropic turbulence, very basic turbulence, like this. The figure shows some vertical structure of such turbulence, isotropic turbulence, in a cubic box. But so velocity field is just like homogeneous isotropic turbulence, but some mean scalar profile with inhomogeneity is applied. So in this case, mean scalar profile is fixed in two cases like this, just like a cosine function, but length scale is different. Then I also evaluated the non-local diffusivity kappa NL like this. Here, just ignore the result of model 1 and 2. Just look at solid line DNS. So you can see the black line diffusivity as a function of y like this. And also, you can see please see the first three lines, DNS, local, and non-local. And we can see that the non-local expression again agree with the DNS result, like this and like this. And also again, local expression overestimates the scalar flux like this and like this. And the right figure for case 2 suggests that when length scale of mean scalar is short, then non-local model, local model significantly overestimates the scalar flux. In another word, due to the non-local property, scalar flux is just decreased. Anyway, non-local diffusivity is validated again. Then I will try to explain the modeling of the diffusivity. For asymmetric turbulence, non-local diffusivity can be written like this: kappa NL as a function of R. R is the magnitude of separation R here, x minus x prime. And from tensor analysis, this tensor as a function of R can be written like this, two terms. But for simplicity, I ignore the second term and just I concentrate on the isotropic term like this, kappa NLR. And kappa NLR can be written by time integral. Tau is just a time separation. And kappa NLR tau can be evaluated using the Green's function g and velocity like this. So the next figure shows the solid line is just a profile of kappa NLR like this as a function of R. Okay. So and also I showed you the time dependence, tau dependence of kappa NLR tau. So please look at the solid line like this, and as for three values of time separation, 0.2, 0.4, and 0.6. And you can see that as time difference increases, the peak value of kappa NL decreases rapidly, say 8, 1.4, and 0.3, like this. And profiles gradually increases, become broad like this. So this suggests that as tau time difference is increases, then profile becomes wider, which means that the spatial non-local effect is increased. So from more wide region, mean scalar gradient affects the scalar flux at present time. Okay. And by following the way of statistical theory of turbulence, I tried to model the non-local diffusivity. So using the statistical theory called the direct interaction approximation, so Krajnan already discussed that Eddy diffusivity given by correlation between U, G, U correlation should be modeled like this. Capital G mean Green's function, and Qij is the two-time velocity correlation, which means just the triple correlation is, how should I say, factorized, just like this, the product of G and Q, like this. And then I will try to model each of two quantities. Then Qij is just a two-time correlation, velocity correlation. And I just evaluated its behavior like this. So this is a function of R. And as time goes on, time increases, slightly decreases. The correlation slightly decreases like this. But you can see that such a decrease is very slow compared to the decrease of non-local diffusivity itself, like this. So anyway, such a decrease is very related to each other. And so this correlation can be analyzed well in the Fourier transform, Fourier spectrum like this. This is just a QIIK is just a Fourier transform of the two-point correlation. QIIK is just a kind of energy spectrum. So actually, when tau equals 0, this is just a energy spectrum like this. So as time goes on, such a spectrum decreases like this in the wave number space, K. So when tau equals 0, this is just the energy spectrum, and red line is the spectrum, famous spectrum, Kolmogorov spectrum, proportional to K to the -5 farad. And also, when this spectrum is normalized by the energy spectrum, we can write down this following picture. And I try to model this behavior. There are several candidates of function of GQK tau. I'm sorry, I write down the QIIK is the product of energy spectrum and GQ term, which represents the time dependence. And this time dependence term, I modeled like this, exponential minus this square term like this. And here U0 is the turbulent intensity, and C omega Q is just a non-dimensional constant. So by considering this behavior of DNS values, red line is just this function. So I determined to model this function like this instead of among some other candidates like this or like this. But honestly speaking, I just simplified the expression of two-point correlation by only energy spectrum only. This is because, as I mentioned, this decay is very slow compared to the non-local diffusivity on itself. So just the mean green function represents the time dependence in my approximation like this. So then we consider modeling the G part of kappa NL diffusivity. Then here, by analogy with GQ, just I mentioned, I also modeled G itself using this same function. But model constant itself is different, but it's the same function. And actually, this function in wave number space is written in physical space like this, just a simple Gaussian function, even for R square. And this Gaussian function is indeed considered as a diffusion process with diffusivity like this. And please note that this diffusivity also depends on tau. So anyway, this is a ordinary diffusion process. But this is just a comment. This diffusion may be analyzed and modeled more accurately from the viewpoint of the fractional calculus if I more accurately evaluate the DNS values and also or examine in more detail. Anyway, this is just a comment. So, and also another modeling of QIIR. This is just a two-point correlation. It is written in terms of energy spectrum EK like this, and I just used the well-known Kolmogorov energy spectrum proportional to K minus 5 thirds like this, with the sharp cutoff wave number. Kc is just a wave number lower limit, I mean energy containing range, and Kd is just a wave number at high wave number cutoff, I mean dissipation range. And we have two model constants. One is for energy spectrum, and the other is for G, mean Green's function, or diffusion constant like this. Then I will show the two results, model 1 and model 2. CK equals 1.7 is actually the well-known value for Kolmogorov spectrum. But I found that this CK is rather too large, so it is decreased like this for model 2. And here, this is the result of the, again, the same figure. And red line is model 1 and blue line is model 2. So for three-dimensional profile as a function of R, maybe two models are slightly different from DNS values. But for this one-dimensional value, model 1 is somewhat under-predict the DNS value. But model 2 agree with DNS like this. And actually, the lower figure, I'm sorry for, I hope you can see the green dotted line here, model 2, also plotted here. And it agrees with the DNS value as well as the non-local expression. So model 2 agrees with DNS. But time dependence profile is rather different. So in time difference profile, model 1 is rather better. For example, model 2 is fairly under-predicted the peak value like this. But you can see that apart from the center region, say you can see that blue line is more close to the DNS value. So red line is just slightly under-predicted the DNS value. This is why averaged value kappa NL under-predicts the kappa NL value by model 1. Anyway, I wanted to improve such a profile again. Then, and also, energy spectrum is useful for homogeneous isotropic turbulence, but it cannot be used directly to inhomogeneous turbulence, such as turbulent channel flow. So towards inhomogeneous turbulence, I just changed modeling of QIIR, two-point correlation. So instead of Fourier transform, scale space decomposition was introduced. So let me briefly introduce what is the scale space means. So here, using some filtering process, I introduced some decomposition in the scale space. Here, U bar is the filtered velocity. This is just a convolution with filter function denoted by G bar. G bar is just a Gaussian filter function. And S, this is actually has a dimension of length scale squared. Anyway, we call it S scale. And U bar, this filtered velocity represents the velocity whose scale is equal to S or greater than S. And by differentiate U bar with respect to S, we can define U hat, which represents the velocity whose scale equal to S. Okay. Then not only velocity itself, but also two-point correlation can be decomposed into like this in scale using integral with respect to S. Here, Q hat is given by this correlation. And also, when R equals 0, then this is just a kinetic turbulent kinetic energy, and it is decomposed in the scale space. I mean the S integral. And Q hat is a kind of energy spectrum, or I call it energy density in the scale space like this. And also, just like a cutoff Kolmogorov spectrum, I introduced the energy density profile corresponding to the column of spectrum like this. Here, instead of k to the minus 5 third, the spectrum should proportional to s to the minus 2 third like this. And actually, this solid line denotes the DNS result of the energy density in scale space as a function of S. And red curve is just a modeled profile using CEST equals 1.9. But for non-local diffusivity, I decrease the constant CS to 1.3. This is the blue dotted profile. Anyway, this is just a figure of energy density, which means that energy is decomposed in the scale space. Okay. Then just I will show you last examples, results. Then blue line is the result of a new model with energy density in scale space. Then three-dimensional profiles is close to the DNS result like this. And also temporal behavior also improved like this by using the new model. And finally, I will show an attempt to apply it to inhomogeneous turbulence, just like channel flow. Okay. And in this case, non-local diffusivity can be written like this as a function of not only y profile, but also x and z directions like this. And also, some anisotropy is expressed in terms of the anisotropy of Reynolds stress itself. And some convection due to mean velocity ux is incorporated in the definition of Rx separation. And also, mean Green's function. This is just a it was just a simple Gaussian, but here some isotropic diffusion effect is introduced using the R. R is just a Reynolds stress tensor. So using the Reynolds stress tensor, some anisotropic diffusion is expressed. Then I will show the final with two pages. So this is the exact value of kappa NL as a function of x streamline direction and y or normal direction at different 3 time differences. So as time difference increases like this, then the strong region just convected in the downstream like this. So contours just convected downstream. And also you can see the profile is elongated in downstream and slightly tilted towards bottom wall. So this is just a evaluate kappa and L. And also next slide is the model of the kappa and L. And you can see that the convection effect is reproduced and elongated and slightly tilted was overall reproduced by this model expression. Okay, this is the final slide and conclusion. So non-local expression for scalar flux was evaluated and it reproduces the S values. And local model tends to overpredict scalar flux when mean field length scale is short. And model for non-local diffusivity was proposed just following statistical theory of turbulence and examined using DNS of homogeneous isotropic turbulence. And model for kappa NLR and kappa NLRT agreed with DNS value by introducing so-called scale space energy density. Okay, that's all, and thank you for your attention.
Thanks, Professor Hamba, for the interesting talk. For the questions, I request the member of the audience to kindly raise your hands and I'll call out your name as they appear on my screen. Okay, Professor Diego has a question. Please go ahead. Please unmute your mic and
Yes, well, thank you very much, Professor Hamba, for a fascinating and very interesting talk. If you go to slide number 13, I might be able to guide my question.
13?
Yes.
30 or 13?
No, 13, 1-3.
1, 3, okay. Sorry. Okay, yes.
That's right. So I found very interesting the numerical constructions of the kernels, the function kappa that you show on the right plot.
Mhm.
So the question I have is that when you approach the boundaries of the computational domain, I guess these are -1 and 1, right? So what I would like to know is what happened in more detail to the kernel, to the non-local function as you approach the boundary. Because mathematically, imposing boundary conditions when you have non-local operators is very difficult. And therefore, there is the idea that the non-local kernels become local as you approach the boundary. And I just would like to know what your numerical simulations show in that respect.
See. Anyway, G itself is a kind of scalar, as I mentioned. G is just governed by this equation. This is a kind of a scalar fluctuation also, but simply source term is different. And I applied the same boundary condition for theta and G, which are both 0 at boundary.
So if you go back to the slide 13, 1-3, that
yes,
means
so,
that the kernel, what happens to the kernel? Because the kernel can actually become more narrow or just...
yeah, in some sense more narrow. Yes, because turbulence length scale itself is narrow near the wall. So narrow means just compared to the, for example, this solid line, just compare this solid line and some other dashed line. Of course, the kernel is narrow near the wall. This is partly because of the short length scale of turbulent velocity fluctuation themselves.
Okay. Okay, thank you. The other question I have is related to the time non-locality, because your more general expressions show that the kernel might depend also on time, having some memory effects.
Yes, you're right.
I don't know if I missed it, but do you have numerical results that show evidence of how the non-locality in time is?
So maybe this figure, solid line, is just a result of this. Not so reliable, or I mean, the time averaging is not enough. But still, we can overall profile. As I mentioned, the peak is rapidly decreases. So then, of course, mean memory effect is, of course, decrease when tau increases. I mean, very long past effect. But at the same time, the space profiles becomes broad. I mean, which means that we can write down the, for example, if tau equals less than 0.1, such as 0.1 or 0.05, then the profile is much narrow, sharp, which means that when tau is very short, I mean very recent past time, then spatial non-local effect is not so large. So tau is large, then spatial non-local effect is large. This is just like a simple diffusion process. When we consider tau is just considered a time, this is similar to say some diffusion process. So it is a kind of a, say, when some researcher already discussed about some diffusion of adjoint equations. Adjoint, I'm afraid, yeah, some kind of adjoint field. And in this case, this is just a simple diffusion process. So does it make sense? So anyway, this solid line represents some behavior for memory effect.
Okay. Thank you very much.
Thank you. Thank you for your question.
I want to add one comment to it, Professor Diego. So the first question that you asked about the kernel becoming smaller, in this case, and also in my studies, I found that near the wall, what happens is that the flow actually becomes local. So I modeled the case of channel flow and quid flow using Caputo fractional derivative with two-sided operators. So I received the fractional order one when I used the data. But had it not be the case that the flow is not local in that region where there is pure diffusion at that boundary, then we would have received a fractional order which was not equal to 1. Does that make sense to you?
Yes, absolutely, because this is something I was sort of expecting, and in my modeling of non-local transport in turbulent plasmas, this is what we actually our approach, that somehow the non-local operator, as you transition to the wall or the boundary, becomes local, becomes more of a local diffusion operator. But
Yeah.
I think this is a very important open problem, because it has to be treated both from direct numerical simulations, theoretical models, and also the mathematics underlying the imposing of boundary conditions is a very subtle issue. Because as you know, yeah, back in 2006, this is when I also used the Caputo derivatives in space to impose well-posed boundary conditions in finite domains for non-local operators. But yeah, thank you for your comment, and thank you, Professor Hamba.
Thank you. Professor Hamba, I have one question. So what is this new model formulation? I didn't see the formulation for the new model.
So sorry, what is your question about modeling? So
Okay. So in your last couple of slides, you developed a new model.
yes, so for anisotropic one, so like this.
Okay. Okay. So
So this is just a say attempt, not full enough. Also, I
okay.
need not only anisotropy, but also some treatment near the wall should be treated.
I see. I see. So you're introducing the term R over there, which takes care of the anisotropy.
So yes, R is the Reynolds stress, and using Reynolds tensor itself, anisotropic diffusion of Green's function is introduced. So this is just a anisotropic diffusion process, like say, for example, streamwise direction diffusion is large, or normal direction diffusion is weak. Then like this, starting from the point source, gradually diffused like this.
I see. This result is very interesting. It feels like the kernel is advecting, and there is some diffusion of the kernel as well. So if I know some initial condition for the kernel, then I can advect it. Is my understanding correct? Can I say that this kernel is advecting in space and time?
Yes, yes, yes. So this
Okay.
is a function of space x, and this is just a example of xy plane only, but it is just a 3 different time.
Yeah, quite interesting. Quite interesting. Okay, does anybody have any other question? Please raise your hand. Or does anybody have some final remark or something, so we can, before we close, you can unmute your mic. Okay, probably not. So I think this is a good point to close this talk. Professor Hamba, thank you very much for the for this nice presentation. The ideas are very nice, and I hope this field progresses along with your leadership and a couple of others that we have in the seminar series.
Okay, thank you very much again.
Thank you.